Parallel RL circuits are very similar to parallel RC circuits, and you'll find that RL circuit problems are solved in much the same way as RC problems. Just as in the RC circuit, EA is used as the reference vector, and the branch currents are used to show phase differences. Now, of course, the resistor does not produce a phase shift, thus IR will be shown in phase with the reference vector EA. The inductor, however, introduces a 90-degree phase shift between current and voltage, but not in the same way as the capacitor. If we plot a vector diagram of the RC circuit, we must show IC 90 degrees ahead of EA because current leads voltage in a capacitive circuit. And of course, the total current will be ahead of EA by some angle less than 90 degrees. Now, this circuit is said to have a positive phase angle or leading phase angle. In the RL circuit, EA is plotted as the reference vector, and IR, of course, is shown in phase with EA, the same way as in the RC circuit. However, since the voltage in the inductor leads the current, or saying it another way, the current in the inductor lags the applied voltage, we must show the 90-degree phase shift caused by IL. It will be plotted 90 degrees behind EA or in the opposite direction of IC. Or current in this circuit is said to lag EA, and it has a negative phase angle. Now, this is really the only significant difference in RC and RL circuits. That is, RC produces a positive or leading phase angle, RL gives us a lagging or negative phase angle. Now, let's review the methods used to solve parallel RL problems. We can find the branch currents by simply applying Ohm's law. For example, in this circuit, if we apply Ohm's law to find out the current value in the resistive leg of the circuit, we take the applied voltage, 24 volts, across the 8 ohms. IR is equal to E over R, or 24 over 8. IR is equal to 3 amperes. Now, if we plot IR on our vector graph, we must show it in phase with EA, because there is no phase shift caused by the resistor. And of course, IR, according to our calculations, is 3 amperes. 3 amperes in phase with EA. And notice we've allotted 3 units on the graph to represent IR of 3 amperes. Now, to find IL, or the inductive current, we would do the same thing, use the same method, that is, apply Ohm's law. IL is equal then to E over X of L, or 24 over 6 ohms, which IL equals 4 amperes. Now, when we plot IL on the vector graph, we must show the 90-degree phase difference. Remember, IL lags EA by 90 degrees, and it is a value of 4 amperes, so we'll use 4 units on our graph to represent IL. Now, the total current may be found by simply measuring the resultant vector when we draw a parallelogram. Simply draw the parallelogram and measure the resultant vector. In this case, we would find it to be 5 units long, or IT, the total current, would equal 5 amperes. Now, angle theta may be found by measuring the angle between EA and IT. In this case, if we were to measure the angle, we would find it to be 53.1 degrees. And notice now that angle theta, since this is an inductive circuit, is a negative phase angle, or a negative 53 degrees. To be sure you realize that measuring this graph is approximate at best. The most accurate way to solve the problem is trigonometrically. Now, since the vector representation can be closely related to a right triangle, Pythagorean theorem may be used to solve for IT, or IT is equal to the square root of IR squared plus IL squared. IT equals the square root of 9 plus 16, or the square root of 25, which of course is 5. So IT equals 5 amperes, the same value we found on the chart. Now, of course, total current, once total current is known, the total impedance of the circuit may be found simply by applying Ohm's law. ZT equals EA over IT, or 24 over 5. The total impedance is equal to 4.8 ohms. which you will note is less than the smallest impedance in the circuit. Now, perhaps one of the most important characteristics of a reactive circuit is the phase angle, which is determined by the ratio of resistance to reactance, and may be determined very simply by using trig functions, which, as you know, are determined by the amounts of resistive and reactive currents in the circuit. The sine of angle theta is equal to IL over IT, the cosine is equal to IR over IT, and the tangent of angle theta is equal to IL over IR, or simply R over X of L. Now, the trig function you use will be determined by what you want to find out about the circuit and what information you already have. For example, the phase angle could be determined with only the reactance and the resistance of the circuit known. In this circuit, the tangent is equal to R over X of L, or 8 over 6. The tangent of angle theta is equal to 1.333. Going to the trig tables, angle theta could be found then by finding the tangent closest to 1.333, which in this case is 1.3319, and that would give us an angle of 53.1 degrees. However, other trig functions may sometimes be more convenient. Many times the cosine is used because it also equals the power factor. Now, let's solve for angle theta using the power factor, or the cosine of theta. The cosine of theta is equal to IR over IT, or 3 over 5, and therefore 0.6. Going back to the trig tables, we find that the phase angle for a cosine of 0.6, the nearest one being 0.6004, is again 53.1 degrees. Now, the advantage of using the cosine, as we said, is that the cosine of angle theta is equal to the power factor. Now, the power factor is the ratio of true power to apparent power. True power is the power actually dissipated by the resistor as heat, and apparent power includes the power stored in the inductor's field that is not dissipated. The power factor is equal to the ratio of IR to IT, which in turn equals the cosine of angle theta. Now, we can calculate the power factor for this circuit by first finding the true power, or the power actually dissipated by the resistor. And we would simply apply the formula, P is equal to I times E. And since we're dealing with the power dissipated by the resistor, we would use IR. So the true power is equal to IR times the applied voltage, or 3 times 24, which is equal to 72 watts. 72 watts is the true power being dissipated by the resistor in this circuit. We could find apparent power by using the same method, the same formula. P is equal to I times E. But since we're dealing with apparent power, we would use the total current. The apparent power is equal to total current times the applied voltage, or 5 times 24, the apparent power 120 volt amperes. You remember that the power is measured in volt amperes, apparent power measured in volt amperes, because all of this power is not dissipated as heat. Well, now we can calculate the power factor by applying the formula. Power factor is equal to true power over apparent power, or 72 over 120. Or the power factor in our circuit is equal to 0.6, the cosine of angle theta. And you should notice that by simply transposing this formula, it would be a simple matter to find either the power factor, the true power, or the apparent power if any two of the three values were known. Well, let's recap briefly. EA is the reference vector, and IL and IR are used to show the phase differences in the circuit and may be determined by applying Ohm's law. IT can be measured from the graph or calculated from the formula, the Pythagorean theorem. IT is equal to the square root of IR squared plus IL squared, which of course is a much more accurate method. Angle theta may be measured from the graph also, or found by using the trig tables. Now, which trig function you use will be determined by exactly what you want to know about the circuit. Total impedance is found simply by applying Ohm's law. Well, I hope that you have a better understanding of parallel RL circuits after this brief review. Good luck.